Let's take a look at the fundamental theorem of line integrals. I want to connect this with the idea of the fundamental theorem of calculus, which can be written as, or we typically write it as, the integral from a to b of f prime of x dx is equal to f of, b minus f of a, where of course f prime of x is continuous on a to b. Now this is also sometimes referred to as the net change theorem, or the integral. If we take the integral of a rate of change, that results in the net change. So let's take this idea and extend it now to line integrals. So theorem, let C be a smooth curve given by the vector function r of t from a, of t goes from a to b, and let f be a differentiable function of 2 or 3 variables whose gradient vector del f is continuous on C. So the gradient is continuous over this smooth curve. Then the line integral over the curve of the gradient dot dr is equal to f of the vector r evaluated at b minus f of the vector r evaluated at a, where obviously r of a and r of b are the, r of a would be the initial and b being the ending point on that curve. Now this theorem tells us that we can evaluate the line integral of a conservative vector field. That's kind of important here because this is implying that we're dealing with a conservative vector field. Simply by knowing the value of f at the endpoints of C. So in 2 space, if I have something that looks like this, and let's say I have this point A, which is right here, which has coordinates x1, y1, and I'm going to end up here at point B, which has coordinates x2, y2, and this path that I take, C, meanders around. Doesn't really matter what it does, but it gets here. So this is my path C. That the value is integral doesn't matter on the path. It's path independent because of the conservative vector field. And all I really need to know is what the coordinates are at B, that's x2, y2, and what the coordinates were at A, that was x1, y1. So this integral, this line integral of the gradient dot dr, in this case, is going to be equal to f of x2, y2 minus f of x1, y1. Again, this path is not relevant. Now likewise, if I extend this out to 3 space, so I have a point here A with coordinates x1, y1, z1, and over here someplace I have B with coordinates x2, y2, z2. The path that I take to get there is not important because it's a conservative vector field. So this integral, kind of running out of space here a little bit. So the integral of this gradient dr is going to equal f of x2, y2, z2 minus f of x1, y1, z1, again, regardless of the path. And this path independence is what is so important when we're dealing with conservative vector fields. Now, just very quickly, it does not take much to do a proof for this one. So to prove this, I'm going to say this line integral is equal to the integral from a to b of the gradient at r of t dot r prime of t dt. This is simply parameterizing, but that's going to equal the integral from a to b of the partial of f, little f, with respect to x, dx dt, it's just the chain rule, plus the partial of f with respect to y, dy dt, plus the partial of f with respect to z, dz dt, and I need to slip in a dt over here. Now obviously this is the 3-space case. So this is going to equal the integral from a to b of d dt of f of r prime of t, that's a prime, dt. This is all this is really saying, but that's going to be equal to f r of b minus f r of a by the definition of an integral, which is exactly what we're trying to prove for the fundamental theorem for line integrals. Now, just as a quick reminder, a vector field f is a conservative vector field if it is the gradient of some scalar function. That's to say that if the vector field equals the gradient of f, and this f is actually referred to as a potential function for cap f. Obviously, this is a vector field, because we use that idea when we're talking about this previous example or this previous explanation.